C. Govindarajulu. Today my topic is breadth first search algorithm with an example. Today my topic outline is introduction to breadth first search, key concepts of it, algorithm steps, example graph for breadth first, applications of breadth search, comparison with depth first search, conclusion. Introduction to breadth first search algorithm. Breadth first search algorithm is a graph transversal algorithm that explores the neighbor vertices at the current depth before moving on with vertices to the next depth. It operates on a graph with weight and is particularly used for finding the shortest path in an unweighted graph. Breadth first search can be implemented using the queues data structure to store the nodes be visited. Key concept of breadth first search. Breadth first search starts a select node, visit all the nodes neighbor, then moves on visit the neighbors of neighbors and so on. It maintains a queue to keep a track on the nodes to visited, ensuring that nodes are visited in order they were discovered. And it is completed and optimized algorithm guaranteeing that it will find the shortest path and unweighted graph. Algorithm step of breadth first search. It is start by enqueuing the initially nodes into the queue and mark it as visited. And this topic is we are studying the queues in data structures. While the queues is not empty, dequeue a node, visit its neighbors, enqueuing the unvisited neighbors and mark them as visited. Repeat this process until the queue is empty, meaning all the researchable nodes have been visited. An example graph for breadth first search. Consider the following graph. Here the A. First of all, we visit A node. Here A node have two childrens. Then we have to print out A and inside the childrens of the A node B and C. Then we visit the B node and B node have two childrens and then inside the childrens of the B node into the queue. Then the elements in the queue are D, E, C. Then we visit a C node. Again C node childrens have F. We have to push the F element into the queue. Then elements are D, E, F. Then print out the one by one. Then we have to prove the breadth first search operation. As example of breadth first search, we have discussed the previous slide. This one by one. Thus A is inserted. We enqueue A and mark it as visited. Next we dequeue A visited in neighbor B and C, enqueuing them and mark them as a visited. Continues in manner, we visit a D, E and LE that order, ensuring breadth first search transversal. Visualization of breadth first search process. Visualization tools like graphs, transversal animations can help understanding the breadth first search process visually. These tools can show the BHS explores the graph levels by level, ensuring the shortest path is found. Visualizing the algorithm can aid debugging and optimizing the BFS implementations. Applications of breadth first search. These commonly used in finding the shortest path, unveiling graphs such as network protocols. It can also applicate social network analyzer, web crawlers and puzzle solving algorithms. And BFS is versatile and can be adapted to variation problem solving scenarios. Comparison with a depth first search. BFS explores a graph level by level, ensuring the shortest path is found, while the DFS explores as far as possible along each branch before backtracking. Both algorithms have their strengths and weaknesses, with BFS being optimal for finding the shortest path and DFS being more memory efficient. Choosing between BFS and DFS depends on the specific requirements of the problems at the hand. Complexity analysis of breadth first search. The time complexity of breadth first search O V plus E, where V is a number of vertices and E is a number of edges in the graph. The space complex BF is also O, V due to the need to store the visited node in the queue. BF is efficient for sparse graph with a low edge to vertices ratio. Hence, I conclude that breadth first search is a fundamental graph transversal algorithm that explores all vertices of a graph by visiting all the nodes at the current depth before moving to the next depth. It is efficient for finding the shortest path in unweighted graphs and have various applications in computer science such as network routing and social network analysis. Understanding the key character implementations and applications of BFS can help in solving variation graphs related problems efficiently, and these are very important topic in the queues. Thank you, sir.